name spelling? MV, right?
MV. All right. So that's one way to describe elements of a language. So let's talk about Bacchus-Naur form. This was another one of these things that like changed my life for a while. NAUR. This is a way to describe the syntax of a language. And with a description in this form, you can write code to parse input and tell you whether or not it conforms to some syntax rules. So the BNF for a language looks basically like this. Symbol colon equals equals. I don't know why I would do two equals.
It's more powerful than normal.
It is. Equaler. So it can be some collection of things or some other stuff or some other stuff. So these things are ORs. Okay. And basically what we're doing is we're going to describe something that we're going to give a name as being some collection of other things. Okay? That's a horribly vague explanation, so let's just do an example. For example, I could say an identifier is equal to a letter followed by more stuff, or it's just a letter. And I'm thinking of an identifier in a programming language, so it's like, you know, count or X or I-17. Those are all valid identifiers.
Variables. So,
What?
variable?
Variable names, yeah.
I can see ident.
So identifier colon equals equals,
Identify.
yeah. So more stuff could be a letter followed by more stuff, or could be a number, or let's say a digit followed by more stuff, or it could be just the empty string.
Would you need to put the empty string in greater than, less than symbols?
It might be like angle bracket lambda or just a lambda. So we could say, for example, a digit equals a 0 or a 1 or a 2. Right, so here these are actual symbols. Things inside angle brackets are the names of things that are defined elsewhere. So a digit is just one of these 10 symbols. A letter would be A or B or Y or Z. So I'm thinking of lambda as just kind of a primitive like that. And so now if I take something like I-17, I can say, is that an identifier? Well, is it a letter followed by my stuff? Well, is I a letter? Let's see, yes, it's an I. That's part of a letter. So I is a letter. Is 17 a more stuff? Well, what is more stuff? Well, it could be a letter followed by more stuff. Is 1 a letter? No, it's not. So it's not a letter followed by more stuff. Could be a digit followed by more stuff. Is 1 a digit? Yes, it is. So is 7 a more stuff? Well, it could be a letter followed by more stuff. No, it could be a digit followed by more stuff. 7 is a digit. Is the empty string more stuff? And more stuff could be this. Yes, it could be the empty string. So up to this point, I've matched an identifier. And I could make a similar BNF for an expression. I will do that shortly. And then I could describe an assignment statement as being an identifier, followed by an equal sign, followed by an expression, followed by a semicolon. And now I have the BNF for an assignment statement in C. An identifier, followed by an equal sign, followed by an expression, a right-hand side, followed by a semicolon. And I could write this for every type of C statement. I could have an if statement, I could have a while statement, I could have a declaration statement, and I could eventually define the BNF for a C program. And it would be, you know, this followed by that, or this other thing, and so on and so forth. We'll pull that up in a bit. So let me show you possible BNF for an expression. So the right-hand side of an equal statement. So expression could be a variable or a number, or left parentheses followed by an expression followed by a right parentheses, or an expression followed by an operator followed by an expression. And an operator is a plus or a minus or a times or a divide.
Or mod.
Or what?
Mod.
Yeah, we can throw in mods. Cool. And a variable let me do a simplified version of a variable. It's a letter followed by a variable 2, or it's a letter and variable 2 is a symbol followed by a variable 2, or just a symbol and a symbol is a letter or a digit or an underscore. And we can define what letters and digits are, but they're just letters or digits. So how does this work? X plus y. So is this a valid expression? It's going to be an expression because it's going to match an expression followed by an operator followed by an expression. The operator is the plus. X itself is an expression because X is a variable, which is just a letter, right? And Y is a letter, which is a variable, which means that Y is also an expression. So this has the form expression, operator, expression. And since this will parse as an expression, and this will also parse as an expression, ultimately this will parse as an expression, an operator, and an expression. So this whole thing will come out of this as an expression. But if I don't have this closing parentheses here, right, if I just have parentheses A plus B with no closing paren, is this an expression still? Well, it's not a variable because variables can't begin with parentheses. It's not a number because numbers don't begin with parentheses. It starts with a parentheses, and A plus B is an expression, but it's got to be followed by a closing parentheses. Right, so that would pass as an expression. And this would pass as an expression because it's a parenthesis followed by this thing, which is an expression, followed by that closing parenthesis. And how do we know that this is an expression? Because it's a parenthesis followed by an expression, a plus b, followed by a closing parenthesis. And that's an expression because it's an expression, operator expression, and that's an expression because expressions can be variables, which can be letters. So a few lines of description here capture the whole gamut of what an arithmetic expression can look like. And you can have arbitrarily complex things. Right, and that will, according to that BNF, that will come out as an expression. So you can look up like the BNF for C, and it's not really all that long. It's about a page and a half of, well, about 2 pages of declarations like this. But you can take any C program and run it through this and tell whether or not it's got valid syntax. And this is what you do basically in the beginning of a compiler. You go through and you check the syntax, and often while you're checking the syntax, you're also recording information. For example, every time that I come to an expression which is a variable, I know I've got a variable in my program somewhere. If I'm writing an interpreter that's going to execute your program line by line and I see a variable like W17, I know, hey, somewhere I need to keep track of the value of this variable W17. So how do I do that? Well, maybe I have a hash table and I make an entry for W17 and I store the value associated with that as 0. And that's where I'm going to store the value of this. And every time I have an expression, operator expression, I ultimately will boil that expression down to either a variable or a number. And if it's a number, I know what it is. If it's a variable, I can go to my hash table and find the current value of that and use that as my expression here, do the same thing over here, apply my operation with a switch statement, and now I've got the value of this, which gives me the value of an expression. And if you put this together just right, it's not a lot of code, but you can build yourself an interpreter or a compiler that will actually evaluate your C code or whatever language it is that you're parsing and compiling or interpreting.
Programming assignment number 3.
Programming assignment number 3, yeah. And a lot of this is you know, so a multiplicative expression is expression times cast expression, expression divided by, or expression percent, and additive expression is plus or minus. And these are done in pieces. This is capturing the priority of operations, right? So multiplication is going to be done before an addition or a subtraction, because it's going to grab that multiplicative expression first. And so this is broken out in order to capture the priorities of these things. But there's C. And if you want to make your own language, right, you start by writing a BNF or some description of the syntax and make a parser for it. Now there are tools out there that will chew on this and make you a compiler. There's a thing called YACC, Y-A-C-C, which is yet another compiler, and it takes a description of a language like this and it builds a compiler basically. And there were a ton of these, and someone made yet another one, and that's what YACC is. And there's Lex, and there's Bison, and there's all these other tools that are part of standard Unix that help you do these kinds of things. I always forget to pull this up ahead of time. Oh, but I don't need to. I've got it here. I don't even know what this is going to do. All right, so here's a short program that's basically doing syntax checking on expressions. And it knows that I'm missing a parentheses there. Or that I'm missing a operator after that y. All right, so this is scanning my input string and parsing it as an expression. And so there's my BNF for an expression, simplified, but it's basically what we were just looking at. And the main program reads a line from standard in, gets rid of the null terminator, calls this function called parse, and if it returns a failure, max string tells me how far it got through the string before it found an error. So I will move over that many spaces and then print a caret saying there's a problem. And the parse function is something that I wrote like decades ago, inspired by something called Tran. It was an assembly language library on the old VAX VMS system, and I fell in love with it, so I ported it to C. And basically it lets me take this BNF and write a series of statements that correspond to this. So my initial state is called parse, and it says I'm looking for an expression, and if I find an expression I'm going to go to state S1, and state S1 says I should hit the end of my string. So this is parsing an expression. What does an expression correspond to? Well, if I have a minus sign, I'll move to state S4, so a minus sign followed by an expression, that's a successful parse. Otherwise, if I have an L expression followed by whatever state 5 is, which says find me an operator, followed by nothing, or if I have a left expression, an operator, and an expression, that's success. And that's capturing this part of my BNF. And so for everything up here, you basically just write down a description of what's an operator. It's a plus, a minus, a times, or a divide. What's a variable? It's an alpha followed by an svar, which is either more variable or lambda. And that's the whole description of it, and then you just run it through this parse program, which is horrifying code. But it basically lets me take all of this syntax parsing and just describe it by translating it into a bunch of state transitions. And the connections between state machines and parsing are plentiful. And we're going to move into state machines shortly, with an eye towards how we use state machines for parsing things. Because what are you doing when you check a BNF? We're trying to find an expression, so we're starting in some state that says I want an expression. Well, first thing we're going to do is say if we have a variable, right, then we succeed. If we have a parenthesis, we're going to go to a new state, which is going to look for an expression followed by a closing paren, right? So 250, we study state machines, we make the big, long, horrible, wide tables, and we do the Q and Q bar and the J and K and all of that stuff, right? And we don't usually deal with flip-flops as computer scientists, but we deal with state systems all the time, right? We deal with stateful programming, and this is one example of where this comes up. All right, so let's, we got about 5 minutes. Let's remember state machines. So how many people here had 250 with me? Okay, so you may have seen this before. So this is the mood machine, okay? So this is very happy, this is happy, this is sad, and this is very sad. And here's our input. 1 equals sunny, 0 equals cloudy. So if we're very happy and it's sunny, then tomorrow we're going to be very happy. If we're very happy and it's cloudy today, tomorrow we're just going to be happy. If it's cloudy and it's sunny, then tomorrow we're going to be very happy. If we're happy and it's cloudy, tomorrow we're going to be sad. And if we're sad and it's still cloudy, the next day we're going to be very sad. And if we're very sad and it's cloudy, we're going to stay very sad. But if it's sunny, we'll just move to sad. And then if it's sunny for a second day, we get happy. And then if it's sunny for a third day, we get back to very happy.
Wow.
So this is a machine that can predict your mood based on the weather. So you feed it the weather and the clock ticks once every 24 hours. So you're in some initial state, let's say you start off happy, and you look at what the weather is, and when the clock ticks tomorrow and you wake up, you've gone either to here if it was sunny, or you've gone to here if it was cloudy. Right? And it predicts your mood based on that, okay? So it's a classic state machine. And we can implement this in software with a state variable and a bunch of if statements. We can implement it in hardware. We won't do that. So this is actually inside most microcomputers. Okay, this is also something called 2-bit branch prediction. This is used inside a microcomputer so that when you get to a conditional branch statement, or when you see a conditional branch statement coming but you haven't executed it yet, you'd like to be able to make a guess whether that branch is going to occur or not. So branch of 0, well, we don't know if the 0 bit's going to be set when we get there because that's 10 instructions down the road, but we'd like to make a guess. And you can use this exact state machine to predict whether or not you're going to take a branch that hasn't occurred yet. So that when you get to that branch instruction, hopefully if you decided it was going to be taken and it's been taken, you'll be fetching instructions from the correct place in memory. Or if you predicted it was not going to branch and in fact it's not branched, you've been fetching instructions that come right after that, and those are the instructions you actually need. Alright, so we will play with state machines on Wednesday. We'll look at things we can do with them, including recognizing types of languages, and that's going to lead us into Turing machines. And Turing machines will be kind of the highlight of, well, the ending point of this course, but I think they're the highlight. So we'll look at Turing machines, what they are. We'll work with writing some Turing machine programs, and then we'll see some of the things Alan Turing did with these theoretical models of computation, and I'll tell you how to make $1 million.
Oh.
Yeah. All right, so I'll see you Wednesday or Tuesday.